but I would like to thank, first of all, Paolo and Mariette for joining in today's event. And before I introduce them, I would like just to say a couple of things about the Thomas Young Centre, if in case some of you are not aware of it. So today's event is about the TYC. Will be a soiree, but it's done in the morning, about modeling mineralization processes. And for the people in the audience that are not aware or familiar of the Thomas Young Centre, the TYC is the London Centre for the Theory and Simulation of Molecules and Materials. And it is made up of around 1,100 research groups from the four main London colleges, Imperial, King's, Queen Mary, and UCL. And it represents probably the largest concentration of materials and molecular molecules in the world. So one of the missions of the TYC is to provide a collaborative environment for materials modelers to interact. And what we do is we organize training events and scientific events, and we organize regularly highlights on specific topics. And clearly, one of the challenges in material modeling is being able to simulate processes occurring in natural environments. And with this in mind, last year we decided that it was time for the TYC to organize a symposium on modeling mineralization processes. And because this is of interest of both fundamental science, because clearly we want to understand how mineral grows, but also it is important for applications such as CO2 mineralization, cementification, degradation, dissolution, construction minerals, and so on and so forth. So therefore, I'm very happy to have two leading researchers on such a topical subject, Mariette Wolthers and Paolo Raiteri. Mariette is from the University of Utrecht, and Paolo is from Curtin University in Australia. So I think the first speaker is Paolo Raiteri. So I will very briefly introduce Paolo. So Paolo is from Curtin University, but originally is from Italy, where he did a PhD in material science at Milano Bicocca. He did a postdoc at ETH, I think with Parallel's group, before going down south in Australia, where he had independent research fellowship position before being promoted to associate professor, and I think now full professor. And now Paolo is an expert in atomistic simulations, and in particular free energy calculation. And his main research interests are, among other things, computational geochemistry, with particular focus on dissolution and growth. So what he will give us today is an overview of his work on atomistic simulation of ion association, surface adsorption, and mineral dissolution processes. So thanks a lot, Paolo, and the floor is yours.
Thanks, Davis, for the introduction, and I'll start sharing my screen. So hopefully you can see it, and yeah, just feel free to interrupt if there is any technical problems, or if you have any questions. So first of all, I would like to thank you all for convening at this unusual time to accommodate for the 8 hours time difference here's the dog between Australia and London. So I really would have liked to be in London and give this talk in person, because I haven't been there in like 5 or 6 years. But unfortunately, Australia still has the border shut, and we are not allowed to travel anywhere, which has been good for us because it's kept us safe so far from COVID. As I was telling before to Davis, we had just our second COVID-related death since the beginning of the pandemic, which was really good, but had a really big impact on our research group. So that photo there was taken in December 2019, and since then 9 people have left the group. They have moved on, finished their PhDs or their postdocs, and we basically have been able to recruit only 2 people since then. So hopefully now, when we all get used to COVID, we will be able to attract more outstanding researchers to our group and replenish all the bright minds that have left. So before starting, I also want to acknowledge the Australian government and POSI for provision of computer time. And
Paolo, we cannot see your slide.
Oh, why not? What happened? Share screen.
Okay, yeah, we can see it now. Yeah, great, thanks.
Can you see it now?
Yeah, yes, we can see it.
I don't know what happened. Okay, so anyway, the work that I'm going to talk about today was done partially by Julie, Alicia, and Alessandro. As Davis mentioned, our research is mostly falls under the umbrella of crystal growth, which most of you are probably familiar with. And we experience the formation of minerals, particularly carbonates, on our everyday life, either in the form of scale on domestic appliances or in industrial environments like this clogged pipe here, or in more pleasant forms like shells and the exoskeletons of many animals. So it's really a wide area of research to understand how these minerals grow in so many different environments, from marine to industrial and controlled environment. And there is a lot of fundamental research to try to mimic, like in the biomineralization processes, in the biomimetic field, or to prevent the formation of scale to improve industrial processes. And despite this formation of minerals is ubiquitous in our lives, we don't really know exactly how it happens. So we clearly know where we start from, which is a supersaturated solution of ions in water, where the ions can appear as isolated particles, small clusters, or bigger clusters, or ion pairs. And we know where we are ending up, like with crystals that have very specific habits or very specific shapes. But what's in between these two extremes is not very well known, because it happens on a very fast time scales and very small sizes. And there are many theories that have been proposed, from classical to non-classical, and the role of the additives has also been widely studied. So I don't really want to get into this big hot debate about whether it is classical and non-classical nucleation. So we'll just focus on the two extreme side. What happens in solution and what happens once we have a crystal that is growing in the presence of maybe organic molecules. The tools that we are using to tackle these problems are those provided to us by molecular dynamics, which I think most of you know what it is about, but very briefly, it's just an iterative solution of the Newton's equation of motion, where the energies and forces are obtained using empirical equations that contains tens or hundreds of parameters, depending on the complexity of the system. So one of the key aspects of molecular dynamics simulation is to use accurate enough force fields that will allow us to make predictions that are comparable with experiments, so thermodynamically accurate predictions. And this is a big part of the work that we do in our research group, so develop this set of parameters. And here is just a snapshot of the force field that we are working on at the moment, where we have significantly improved the carbonate water interaction, which allowed us to also improve the ion pairing information. Hopefully we will finish all this work and publish it by sometime this year. However, despite the efforts in developing force fields, because they are based on empirical equations, it is somewhat hard to capture all the complex electronic properties or the complex features of the real materials, because they lack polarization, for example, and they are not able to form or break bonds, so we don't have any reactivity. So though reactivity is not something easy to fix, polarization is somewhat easier to fix. So we've started using more regularly these amoeba polarizable force fields, where all the atoms are described as point particles with a multiple expansion of the charges up to the quadruple, plus it includes atomic polarization to mimic the presence of electrons in the system. Most of the simulation I will show today are done with this force field using the OpenMM program, which has been augmented with Plumd, which is a plugin to calculate free energies using a selection of reaction coordinates. And here there is a nice movie made by Giovanni about how metadynamics work, which is the main tool that we'll be using for calculating free energies. So one of the simplest things that you can do in this space with metadynamics is to calculate the ion pairing free energy, which can be described fairly simply both in the simulation and with this scheme here, where you have two ions that come together, each of them carrying their own hydration shell. And when they come into contact, the system goes through a dehydration process when some water molecules are removed, and then when there is nothing in between the ions, they form a contact ion pair. And this process is described by this minimum free energy path here, these black beads in here, in this two-dimensional free energy space, where we have two collective variables, the magnesium carbonate distance and the magnesium water coordination number. And so you can see that when the ions get closer to each other, the coordination number decreases until we form a monodentate or a bidentate ion pair. This is very nice, something that everyone knows and it's easy to explain, but it's not particularly useful in making a connection with experiments. So something that is more useful is if we take this two-dimensional free energy profile and then we integrated out the magnesium water coordination number, we can get then a one-dimensional free energy that then can be used to calculate an association constant and an association ion pairing free energy, which is then something that can be compared directly with the experiment because they will have the same reference state. And this is something that we normally do as a first step when we test the force field to make sure that we can reproduce experimental known properties, for example, like the ion pairing. However, it can be also used for some more or maybe less usual applications, like we did, for example, in this work in collaboration with Dennis Gebauer, where they did some experiments at below pH 9 to study the formation of calcium carbonate nanoparticles. And although in solution bicarbonate is the most likely and by far the most abundant species, all the precipitate didn't contain any significant amount of bicarbonate. So one of the hypotheses that we put forward was that it's because when bicarbonate gets into contact with calcium, the acidity of the bicarbonate increases. So it is more easy to remove a proton from bicarbonate. And so in the precipitate, you actually have only carbonate. And to prove that, we built these thermodynamic cycles where the vertical lines are ion pairing free energies calculated with the process that I described in the previous slide. And instead the horizontal line, this is the experimental deprotonation energy for bicarbonate. And so by building this thermodynamic cycle, we can suggest that the pKa of bicarbonate decreases by about 2 units every time one calcium gets into the contact with bicarbonate. So the acidity of bicarbonate goes from 10 to 8.6 when it is in an ion pair and to around 6 when 2 calcium are actually bound to it. So this suggests that what they see in the experiment that are done at around pH 9 is that when the calcium bicarbonate come together, the bicarbonate very easily loses the proton. And so every precipitate will have mostly carbonate. So this was a very nice application of this simple ion pairing process in conjunction with the thermodynamic cycle and S's law, which is a fundamental law of thermodynamics. So another interesting thing that we found by using this ion pairing is that the water exchange of water around magnesium becomes more favorable when magnesium is actually in an ion pair. And this was shown both using the amoeba force field and a new rigid ion force field, so a non-polarizable force field. And by calculating again the free energy as a function of magnesium water distance and the minimum free energy path to go from the separated ion to the contact state, we could immediately measure or calculate what is the free energy barrier of this. So keep in mind that the free energy of the system does not change when a water molecule leaves magnesium because another one comes in. But when we calculate the free energy as a function of the distance between magnesium and one specific water molecule, because that one molecule is now a special one, the free energy is not the same when the water leaves, because that is just like an ion pairing process. However, this is not particularly key for the barrier, because the barrier will be the same in all regards. So we can see that the barrier when the magnesium is in contact with the carbonate decreases by about 8.5 kilojoules per mole, according to the amoeba force field, or even more by about 18 for a rigid ion force field, which this would suggest that the water exchange rate will increase by at least a factor of 50 or by a factor of 2000 if the rigid ion force field was giving a better prediction. We would think that amoeba is more reliable due to the presence of polarization and the fact that it is closer to the experimental value, but it's very difficult to measure these exchange rates experimentally. And there is a bit of a mixed information suggesting that some ligands may increase the water exchange rate and other may decrease this, but there is no experimental information about magnesium and carbonate per se. So we would offer this as a challenge for experimentalists to be able to measure this and validate our prediction. So if we now move at the other extreme of the spectrum, so once the crystal has already has already been formed, and we want to see if we can say something meaningful about how the crystal grows and how small organic molecules can modify the growth of this crystal. So we performed a series of calculations using, again, metadynamics to calculate the free energy of adsorption of various species, both on the flat and on the stepped surfaces of calcite, using the vertical distance from the surface and the coordination number of the adsorption site as collective variables. Each simulation is of the order of 300, 500 nanoseconds, depending on the case. And yeah, we'll see what we get. So the adsorption on the flat surface is not particularly exciting, and this was expected. It's nothing really new. So both force fields predict a fairly weak binding of anything on the surface. And this is, I'm talking about a pristine, defect-free surface of calcite. So there is nothing really for the system to anchor. And it is also well known that the surface has two tightly bound ordered water layer, which are very hard to displace. And so they form a repulsive barrier, if you want, for the adsorption of any small molecules on top of the surface, because some water has to be replaced with the ligand groups, and that is generally an unfavorable process. However, one would expect that maybe there is a stronger binding at the step edges, because there the water structure is disrupted, and so there is a less tightly bound layer. This is really not 100% true, because there are some pockets where the water really likes to stick, and the exchange rate at the step edges may be even slower than on the flat surface. And so these free energy calculations are a bit more expensive, because they have to be run first for a bit longer to exchange the water. Plus now, because we have broken the symmetry of the surface, there are 4 adsorption sites for each species on the opposite charge. And so this makes the calculation already 4 times more expensive, because you have to probe for different sites. The first thing that we notice is that the constituent ions, so calcium and carbonate, have a fairly good binding of the order of 10-15 kilojoules per mole, which is about 3-4 times the thermal energy, which means that the ions want to stay there and want to nucleate a new kink to start the next step and progress the growth of the material. While these small organic molecules seems to have a fairly weak or fairly modest binding, apart from maybe glycine on one of the 4 possible sites. So this would probably suggest to us that these molecules are not really affecting the growth of the steps of calcite, which is not consistent with the experiments, because it has been shown that these molecules actually have an effect as a growth inhibitor or growth modifiers, and they will change the velocity of these steps. However, we have to keep in mind that we are now dealing with the perfect steps, so there is no kink, while in the real system, when it grows, one of the steps then the system has to go through is the nucleation of kinks and then the propagation of the kinks. So if these molecules attach at the kink site, they may stop the growth, or they may slow down the growth of the step. So this could be one of the explanations for how these molecules interact with calcite. So we started working on this, but as you can see, these calculations are already fairly expensive. And then if we break the symmetry further and have the kinks, we now have to do 8 calculations for each molecule, which would make it fairly impractical. Plus, I would like to draw your attention on another small feature here, that for those of you who have done free energy calculations before, every time you see a sharp feature like these ones here marked with a star in a free energy profile, that's a clear indication that some important collective variables have been missed. So in this case, we already used 2. We already used the distance and the coordination number, even if the coordination number has been removed. But even when we also looked at the 2D free energies, we still had these sharp features. And then we had to actually go to 3 collective variables to describe the absorption of acetate and glycine. And to show you why this is, I have this messy, busy slide here, where I'm showing now a three-dimensional free energy profile. So each color here is an isosurface of constant free energy. And the 3 collective variables that we used were the distance from the surface, the coordination number of the absorption site, and then we added the glycine orientation that was calculated as the projection of the carbon-nitrogen bond on a vector that was normal to the step edge. So if we look at now how the absorption process happens, we have the molecule that comes close to the surface and stick at the edge of the step in this black spot here, which is like one of the first deep minimum on the surface. Then the next deep stable state is when the molecule has moved a bit closer to the surface, but still solvent separated from the absorption side. And now it has changed its orientation, which is shown by the fact that it moved along this axis here. So once it is in this state, to form a contact ion pair with the absorption side, it has to go to this narrow channel here, where the molecule has to simultaneously get close, rotate a little bit, and then the absorption side has to dehydrate. So the free energy barrier here is about 40 odd kilojoules per mole, which is more than 10 what is shown here. And as you can see, because this is a very narrow channel, the entropy of going through that is fairly limited. It's fairly small, so the free energy barrier is very high. So it's an extremely unlikely process. And we would not be able to describe this correctly if we were using only 2 collective variables. So the more complicated the molecule gets, the harder it will be to use simply use metadynamics and the distance from the absorption site to calculate these free energies, because the number of collective variables would just explode and will make it absolutely impossible. So we started looking at an alternative approach to do this, where we use now free energy perturbation to make the molecule disappear. So to decouple the adsorbate molecule from the system and go into a state where the molecule is in the gas phase, and now the system is pristine. And then we can transform this into a gas at 1 molar solution and then put it back into water to build the thermodynamic cycles that will take us from the adsorbed state to the molecule in a 1 molar solution, which is the standard thermodynamic reference state. So this conceptually works, conceptually it's easy, but there are a lot of issues in this. First of all, the main one is the eval summation, which is something that we have to use to run our simulations and to make them affordable. And the eval summation requires that there is no charge in the system or no permanent dipole in the system. If this is not the case, there are correction terms that allow us to run simulations with fixed total charge, but there are no readily available correction terms if we change the charge state of the system throughout the simulation. So if we make our acetate disappear, the charge of our system will go from -1 to 0. And then we don't know how to correct this, because this is a correction that depends on the size of the system and on the relative fraction of water and the calcite, because they have a very different dielectric constant. So there is no way to find this. And the only solution would be to make the system increasingly larger and then extrapolate at infinite size. But if we are running a simulation down here with a very small system that already takes a week because we have to run 500 nanoseconds, and then we make the system 16 times bigger, it's just going to take forever. So we've been exploring some alternative solution to this. So either removing neutral species and keep the charge of the system constant, so we don't have to worry about this, or to exploit a cancellation of unknowns. So to take the difference between two numbers that both contain the same correction in the hope that it will actually be exactly the same and cancel out, so that we can still use our Ibal summation with small system and be able to calculate the binding free energy of this molecule. So we've been testing this in the last few months, maybe 8 months, with sodium chloride, and we think now we have a thermodynamic cycle that allow us to calculate the binding free energy of molecules and reference them to the correct thermodynamic state. So to prove this, we calculated the dissolution free energy of sodium chloride using the Young and Cheatham potential, which is very well known. It has been studied to death, and there are plenty of computational study out there that we can compare against. Particularly this one from Aragones and Vega, and this one from Mester, where they calculated the chemical potential as a function of the concentration and compared it to the chemical potential of the water, of the solid, and they also did a direct coexistence calculation. So two completely different methods to calculate the same quantity. So hopefully this provide us a good reference. So our procedure that we can then be also applied for adsorbate is to start from a slab, or in this case of sodium chloride, that has a kink. And if we remove an ion pair from the step edge, our final state will be exactly the same as the beginning, because it will be a kink with the same termination where we started from. The only difference will be that the system is slightly smaller, and so there might be some small fine size effects. But the free energy to take these two ions and put them into water should correspond exactly to the dissolution free energy of sodium chloride. So our procedure goes by adding some spring constants to keep the system where we want it. So we calculate the free energy to add some harmonic restraints to these 4 atoms. Then we use free energy perturbation to decouple the solute, in this case our sodium at the end, from the system. So we have an harmonic oscillator here and our sodium chloride surface. Then we transform our harmonic oscillator to an ideal gas, and then we put our sodium back into solution. And then we remove the springs to close the cycle. So if we repeat this for sodium and chloride, we get these two free energies for the dissolution of the two ions, which add together give -6, which is very close to the values reported by Aragones and Mester. So we think that now we have a working protocol that involves all the standard state correction, translation of free energies, and anything you want to calculate adsorption free energies of charged species and reference them to the standard state. So I think I'm running out of time, so I just want to conclude this talk by summarizing what I have shown, hopefully. So hopefully I convince you that it's important to have reliable and calibrated force field to ensure a quantitative prediction of thermodynamic properties that can be calculated experimentally and that we can use as validation and then as a predictive tool. Hopefully I also showed that we can build some thermodynamic cycles using S's law to calculate quantities that sometimes may not be accessible to direct simulation, like for example, the pKa of bicarbonate, or to validate and cross-check our method by comparing the solubility and the dissolution free energies with other techniques. Hopefully maybe I didn't touch to this very deeply, but polarization is very important, and using an amoeba polarizable force field, we think gives much more reliable and quantitative data than a non-polarizable force field. Unfortunately, the drawback is that the calculation is maybe 5 times slower, so it will require more computational effort, although OpenMM works on GPUs, so it is fairly efficient. And finally, the last point I briefly touched on is that eval summation can introduce severe artifacts, particularly when the charge state of the system changes during the simulation. And something that I didn't have time to talk about is that the same problems with the eval summation come out if one wants to use external electric fields. And if you're interested, there is a reference there of a paper that we recently published. So thanks everyone for listening. Thanks again to the Australian government for support, Policy Supercomputer Centre, all the people that were involved in this. And hopefully I showed you some pretty pictures, some successes of simulations, and also some pitfalls and some things that you have to be mindful about when you run this simulation. Thank you.
Thanks a lot, Paolo. Very nice, very inspiring talk. So I would like to ask people if they've got any questions for Paolo. We've got a few minutes before we go to Mariette. You can unmute yourself, or you can just write on the chat. So while you do that, I would like just to ask Paolo, at the beginning of your talk, that's not the beginning, but when you talk about your results on magnesium, magnesium dehydration, and you show that carbonate could in fact accelerate magnesium dehydration. Have you also, so I've got two questions. First of all, do you think that this could help explaining the dolomite problem in a way?
So that was the inspiration for trying to do this, to try to understand, to try to say something meaningful about the dolomite problem. It is a first step, so it will make the magnesium carbonate aggregation faster if we remove the water. So we had seen that. How much of an impact it has is difficult to say, because the dolomite often grows in the presence of anything organic, bio, microbes, living organisms. So it can be really anything, but well, it's a step to try to address that problem. We have seen.
There is a question from Alston from Quimbery. Hi, Alston.
Hey, there is. Paolo, very nice work.
Hi.
Nice
Hi,
to see
nice to meet you.
I don't know how many years when I saw you in the Cavendish. Yeah, it's a long time.
Yeah.
Paolo, I was very happy to see that the amoeba force field is, you're using that, because it's nice to see that the polarization is important. We've been knowing that for a while, but it's clearly showing itself here. One question I had about the way you used amoeba is you have to get multipoles for this force field. Now, which method did you use? Because sometimes the choice of method can make a bigger impact than putting in.
We try to follow the recipe in the original paper. So we do a calculation with Gaussian, I think MP2 at the end, and then we use GDMA from Anthony Stone to get the multiples. It is a bit fiddly in some places, because you have to decide which polarization groups and which atoms are grouped together in the same polarization group. So we have done a few tests, and then in the end, we chose the one that gave the best results in terms of pairing free energies, salvation free energies, and everything that looks sensible really is what, in the end, is a force field. So if the parameters work and give reliable answers, that's all we care.
Well, the reason I ask is because I've been working with Jean-Philippe, and we are trying to use a different source for these multipoles, which is systematically more accurate than the GDMA. So, but of course, using the GDMA is not a bad.
I'm happy to try it. If you want to put the reference in the chat, I'll copy it down, and then we can give it a go.
Yes. Okay.
Thanks, Alston. I've got another quick question from Greg Chas from Quimbery. Hi, Greg.
Trying to find the right button here. There. You know. Paolo, thank you for this chat. Just a comment. It's very nice to see the word free energy, which implies that entropy is being considered. You know,
we try.
You say like that, but I'm battling the engineering community myself with stuff related to mineralization. They say, "Oh, don't worry about it. Those are small effects." I said, temperature, you know, organization, crystallization, not crystalline. So just to mention, very nice to hear that. So you're saying force fields at the same time, you're saying free energy. So
thanks
for including that. So it's nice to see that. The glycine is very interesting. I started out working on those, and we're starting to see peptides cropping up, you know, amino acids and peptides cropping up into material science, inorganic areas. So, you know, it's very interesting. Also, I saw you had mentioned Tony Cheatham's work there. It's nice to see one of Tony's papers. I said, you know, you're aware, I guess, of Tony's work. And
yeah, it has a lot of work.
Yeah, you know, I know Tony. So no, just a comment that it's nice to see this whole sort of mix of stuff coming together. And, you know, I think that's probably what's going to formulate a lot of solutions, whether it's geochemistry, material science, or otherwise, is, you know, borrowing from one another, solvent effect, free energy, you know, these kind of things. It's nice to see that sort of, you know, myriad of techniques or considerations coming together. So thanks for that.
If you want to convince your engineering
entropy
colleagues about the importance of entropy, you could just look at the experimental data on the ion pairing free energy.
Yeah.
And the delta H is positive. So the ion comes together because of entropy, not because of electrostatics. And that's experiments. It's not simulations. So
that's where temperature starts to matter, you know, T times that delta S thing. Yeah. Great. Okay, thanks.
That's correct. So I think, I mean, if you want to ask your question to Paolo, please, you know, write on the chat. But now I think we go now to Mariette for a talk. So next speaker is Mariette Wolthers. So Mariette is from Utrecht University. Mariette she studied petrology at the University of Amsterdam, and then she did a PhD in geochemistry at the University of Utrecht. And this was followed by a PDRA position between Grenoble and Utrecht, folled by an independent Venier research position at Utrecht. And then she actually came to the UK to do an advanced NERC fellowship and moved back to the Netherlands to get a faculty position at the Earth Science Department, at first as an assistant professor and then as an associate professor. So Mariette at the moment holds a year consolidated grant for the project Crystal Clear to research how minerals are formed under realistic natural conditions and not in ideal conditions. So Mariette is a geochemist by training, but has got quite a good understanding of theoretical methods, both from an atomistic level, then a microscopic geochemical level, and she links that with synchronous-based spectroscopy. So, and in fact, this I think is I believe this is the topic of our talk today. So I look forward to hear from Mariette about her recent work. Thanks, Mariette.
Thanks, Devis, for this kind introduction. Can you hear me?
Yeah, we can hear you.
Yeah, and just checking that you can also see my...
Yes, we can see you.
Desktop, great. And can you see my cursor?
Yes, I can see that.
Yeah, cool. So thank you, Devis, for the invitation to come and present some of the work that I've been doing. I would like to talk about how minerals grow and dissolve, and I'm going to show you how we link simulations to experiments, and the focus will be on calcium carbonate, one of my favorite materials to work on. And as Devis said, I'm by training actually a geologist, and then I got through geochemistry experiments into the modeling and to the smaller and smaller scale, and that's also why I came to London for a while to learn the molecular dynamics techniques. And so it's one of the different techniques that I use to try and understand earth science questions, geochemical questions. And I would like to start with a big thank you. I'm going to present work from my PhD students, Priyanka and Yanu. And I will close with some work from Sergey. And Sergio has been a key person in the research group, also in the collaboration with Yanu. He has been trained in London as a PhD student in MD simulations. And there's many other people I would like to thank, including our host of today, Devis. Okay, in this talk, I want to first zoom in and then out again. So I'm going to start at the micrometer scale and look at calcite dissolution, and then go to atomic scale and show you some MD simulations on pure and magnesium calcites. So again, there's also an important role for magnesium in this talk. And then I'm going to zoom out again, and we're going to look at calcium carbonate nucleation and growth from the atomic back to the micrometer scale. So why look at calcite? Paolo already gave a very good introduction, so I guess you're familiar with that. In essence, it's a rock-forming mineral, it's a scale-forming mineral, and it's industrially very relevant as, for example, a carrier mineral in pharmaceuticals, in paper and glass industry, and so on. And why look at calcite dissolution? Well, from an earth science perspective, it's essential because it's the main mechanism that buffers the ocean pH against ocean acidification. So the dissolution of calcite consumes the CO2 that's going into the ocean and keeps the pH decrease a little bit more gentle. It's an important mechanism for CO2 storage. The dissolution of the carbonate minerals alters rock permeability, which is essential for carbonaceous water-bearing rock layers or sediment layers, and oil and gas. And it's also a mechanism to remove scale. Here I'm holding a little calcite crystal in my hand, and you can already see different features here, little textures on the surface. And if you're going to zoom in to the nanometer scale and the micrometer scale, you see these textures as well. And if you're then looking at dissolution close to equilibrium with increasing undersaturation, the first mechanism you will observe when calcite dissolves is the gentle stripping away of different atomic, so monolayers or a few layers at a time. And this is just sketching calcium and carbonate groups in the crystal. You also see that there are acute edges and there are obtuse edges that are important to consider. And if we go to more strongly corrosive solutions, we will see that edge bits start to nucleate, so little holes in the surface, with the layers spreading, ripping away bits of the surface, or deeper edge bits can form where steps are going to drag away calcite more rapidly. So this is the step wave dissolution mechanism, where trains of steps move and strip away the calcite. And in even more strongly undersaturated conditions, solutions are known to eat their way through the solution, and this is a process that we call wormholing, that we can also follow with, for example, micro CT experiments. And if we look at calcite dissolution rates, of course we can obtain it in the bulk. So just bulk experiments, calcite powders, for example, in columns or beakers, and then see with time how much can dissolve under certain conditions. But we also tend to look at this in the micrometer domain, for example, in this case with vertical scanning interferometry, where you can observe the topography of the crystal surface on the micrometer scale, and you can determine the material flux away from the surface, because you can see how much material disappears from the surface, and you can then map out how these fluxes vary with the topography. And if you then plot this in a rate spectrum, so this is the dissolution rate on the x-axis, and on the y-axis is the frequency, how often do specific rates occur at a surface, you can see that there are rate spectra that characterize different parts of a crystal surface, where sometimes you see this clear optimum and sometimes broader bimodal or more dissolution rates occurring in the frequency domain. Now, the question of the work that we did with Priyanka was to see what actually is the contributor to these rate spectra. So it was assumed that it's the reactivity of the surface that varies with topography. But actually, if you look at these kind of experiments, there is flow along the surface, so there is hydrodynamic influence, and so there must be a variability of transport around these and along these rough surfaces. So we wanted to tease out that contribution from the rate spectrum. And so what we did was we connected with Cornelius Fischer and this group that can do this vertical scanning interferometry. And this is a topography map that they measured, and they measured for specific areas the rate spectrum for this area. And these are the experimental data where you see different rate spectra for the different areas, locations 1, 2, and 3. And we implemented the measured topography in a virtual flow cell, which was identical to the one that they used in the experiment with the same flow velocity. We observed that there is some kind of vortex in the cell, and this area here is where the experiments were done. And that's also where we imposed either topography 1, 2, or 3, and then measured how fast the calcite dissolves. I think you can hear one of my cats who wants to come through the window, but I'm going to try and ignore it and not be distracted. Okay, so if we first look at a perfectly flat bit of calcite in this experimental area in the flow cell, and we impose a single dissolution rate, which was obtained from bulk measurements, we see that over this area of 21 by 21 micrometer, there's no variability in the dissolution rate. And if we then make a profile from P to Q, and we look at the slice of solution above the surface, so the surface is sitting here, we see that there is a diffusive gradient away from the surface, which is expected. So there's a little bit of a buildup of the dissolution products close to the surface. And here where there's more advection, so the solution drags away the dissolution products, we see lower concentrations. And when we then impose topography number 1, and we keep the same single dissolution rate, we have this topography, and over this topography, we see variability in the dissolution rate. So in the high areas, let's call them the plateaus, of course it's on the micrometer, we see these red areas which are closer to the effective flow, so we will see higher dissolution rates, while very intuitively in the deeper areas we see a much lower dissolution rates in the blue colors, because there is a buildup of the dissolution products, because here diffusion is more dominant as the transport mechanism. And so this buildup variability of the dissolution products causes a gradient in the degree of undersaturation over the surface, and therefore variability in the dissolution rate. Now, the question is this what we see as the rate spectra from the vertical scanning interferometry? Well, there is a little bit of a rate spectrum evolving in our simulation. So in blue line here is the results for the no topography area where we have a single rate. And if we have a rough surface with just the single rate, the results I just showed, we see a broadening. So we see a little bit of a rate spectrum evolving, but it is no way near to the green line here, which is the experimental rate spectrum. So the variability in the hydrodynamics at this rough surface is insufficient to explain the observed dissolution rate spectra. And we have to impose, actually fit our dissolution rate over the surface to reproduce the rate spectrum that is observed experimentally. And so what causes dissolution rate spectra? There is a little bit of variability in the transport over the surface, but the main contributor is variability in the surface reactivity. And if we then take the fitted rate spectrum that we obtained from simulating location 1, and we also test this for topography 2 and 3, we see that in the yellow line here, we have rate spectra that we get from our developed model without any further fitting. We cannot really perfectly simulate what was observed experimentally in the locations 2 and 3. So this suggests that each of these topographies actually has its own unique fingerprint rate spectrum, and it is very much defined by the surface topography. And so what causes this variability in reactivity? Well, to illustrate this, I would like to go and zoom into the mechanism of dissolution, which is the extraction of the calcium and the carbonate ions. And this is results from molecular dynamic simulations. I will tell a little bit more about that later. And this is for a pure calcite surface with a little island on top. So there's some topography. And so we have calcium ions in the flat face and on obtuse and acute edges and on corners. And then we measured how much energy it takes to extract these ions from the surface. Now, if the calcium is sitting in an atomically flat phase, then the energy we need to extract it is this green line. And so here is the calcium sitting happily in the surface, and up here it's fully solvated. And we see that we need about 200 kilojoule per mole to extract calcium out of the surface when it is completely flat. And here in the black line, by the way, is the water density close to the surface, which is of course also highly structured until it goes to a bulk density. If we then look at calcium extraction from the edge sites, we need about 60 to 75% less energy to extract the calcium from these edge sites. And that also varies depending on whether we are talking about these acute steps or about the obtuse steps. And then if we look at calciums that are sitting in kink sites or corner sites, then we need even less energy. We have a reduction of about 80% of the energy to take them out of the surface. And so this is a way to quantify the impact of surface topography to understand what we see at the micrometer scale with this relationship between dissolution rate spectra and the surface topography. And so to summarize this first part, the variability in hydrodynamics over rough surfaces is insufficient to explain the broadness of the dissolution rate spectra that we see in the experiments. And the dissolution rate spectra therefore reflect the variability in the surface reaction reactivity, and that depends on topography and reflects the free energy landscape at this surface. And therefore also explains why it is unique for different topographies in the same material. Okay, I would like to zoom in further and now move to the next topic of the talk, which is the magnesium calcites. And so I already showed some of the results from this work within the context of the previous topic. But the aim of this work was to understand the nonlinear impact that magnesium has on the solubility of calcite. And this was performed by molecular dynamics by my PhD student, Young Centre. And so to give you, those of you who want a little bit of detail on the MD methods, these are classical molecular dynamic simulations where we wanted to characterize the interfacial water. We looked at the deformation within the crystals and the surface energies and the extraction free energies. The simulations were performed in lamps with these force fields with a 0.9 nanometer cutoff for the van der Waals and an additional tail in the van der Waals in this part of the force field. And the simulations were run for 10 nanoseconds, and you can find more details in the paper here. This is an example of the configurations that we were looking at, a little calcite crystal with one or more magnesium substituting for the calcium. So I hope you can see it. There's some purple magnesium. So this was the high magnesium crystal replacing the green calcium ions with a water layer on top. So this is the size of our little calcite slab. We had just over 4,000 water molecules, and we are looking at the 10-14 calcite phase, which is the dominant exposed calcite phase in most of the experimental work because it's the cleavage plane. So if you would hammer down a bit of calcite crystal, you will get these 10-14 phases exposed. And you can then do, for example, the vertical scanning interferometry on this. We looked at pure calcite, low magnesium, where we just had one magnesium in the surface, and the high magnesium with 30% magnesium randomly distributed in the calcite. And this is about the maximum amount of magnesium that you can find in natural magnesium calcites in system Earth. And we looked at both the flat phase, and we looked at calcite with an island on top, and either pure or high magnesium calcite in that case. We did unbiased free energy profiling with the plumed plugin in lamps, and Janu developed it with more than 60 overlapping harmonic umbrella potentials and Some of them had to be very narrow to keep the calcium from moving perpendicularly away from the surface. She used a weighted histogram analysis method to then calculate the Helmholtz free energy of the calcium extraction. We also looked at many other properties, but I will focus on this extraction predominantly and show a little bit of the other work as well. And we considered calcium fully solvated when it was about 1.3 nanometer away from the surface. And so here I'm comparing high magnesium calcite versus the low and the pure together, because the low magnesium actually in most of the properties didn't really differ very much from the pure calcium. So the single magnesium didn't really impact, for example, the water density in the interface. The red and the green overlap completely in this water density away from the surface. But in the high magnesium, we see that the water is drawn closer to the surface. So we see a higher water density closer to the surface. We also observed a disruption of the hydrogen bond network, higher water exchange frequencies, which was surprising to us actually, and a faster diffusion parallel to the surface. So, and this is a diffusion of water parallel to the surface. And so in general, the low magnesium was very similar to the pure calcite. And this plot you've seen before, this is again calcium extraction from the surface. This is the pure calcite and perfectly atomically flat. So again, here, this is where the calcium is sitting in the surface position, and here it's fully solvated. And if we then compare this green line, it's also here in the low magnesium and here in the high magnesium, for reference, the same line. We see that calcium extraction from the calcite surface, purely atomically flat, needs in general a little bit extra energy. So it's a bit harder to take the calcium out of this surface. While in the high magnesium surface, it's more variable and it depends on the position relative to the magnesium ions in this surface of the calcium that we're extracting. And if we then look at the impact of the surface topography again, so if we look at calcium extraction from the edges, and this is only comparing the pure, which are the dashed lines, to the solid lines in high magnesium, we see that in the edges, in the acute edges, we see that the energy is increased. So it's harder to take out calcium from this edge, which we think makes sense because we know from experiments that magnesium incorporation during calcite growth occurs through the acute edges, because magnesium is a little bit smaller than calcium. It likes to go and sit in these confined acute edges and stabilize, apparently, these edges compared to the obtuse. And so if you grow calcite in the presence of magnesium, you will see that the zones where the acute edges generate the growth are enriched in magnesium relative to the obtuse side of the crystal. And in the obtuse edges, we see that it takes less energy to extract the calcium from the edges. And both corners, obtuse and acute, are also showing that the pure needs more energy, and so it's decreased by the magnesium presence in the surface. So in 3 of the 4 types of locations, the dissolution is easier in the high magnesium crystal. And so I said that the idea of this work was to get an understanding of the nonlinear impact of magnesium in the solubility of calcite, and that's plotted in this graph. So here on the x-axis is pure calcium carbonate, and we're increasingly having more and more magnesium in this in calcite crystals. We see that the solubility, so this is the log of the solubility constant, also shows this nonlinear behavior that I mentioned before. So pure calcite has this solubility. With a little bit of magnesium incorporated, we see a little dip in solubility, and then we see that solubility increases. And this has been puzzling for quite some time. And what we see in our MD simulations kind of gives an insight into this kind of behavior. If we look at what we saw for our low magnesium, we didn't see a lot of impact in surface energies. If you look at the whole surface and not in the interfacial structure of the water, and also the crystal structure was not really deformed. But we do see that it takes more energy to take calcium out of the surface. So we can say that the edge pit nucleation energy has increased. So it will be harder to generate little dents in the surface that can then be the source of the dissolution mechanisms to strip away the surface. So it makes sense that at low magnesium incorporation, there's a decrease in solubility from these simulations. While at high magnesium systems, we see the crystal is actually also deformed. It's thermodynamically less stable overall. And we see that in particular, the edges and the corners and the kink sites can dissolve much more easily. So this results in a higher solubility and more facile edge pit nucleation. And then to move on to the last part of the topic, which is calcite or calcium carbonate nucleation and growth from the atomic to the micrometer scale. This is work that is from the Crystal Clear project, where we are looking at the impact of the cation-anion ratio in the solution on the nucleation and growth of ionic crystals. And again, we're now focusing on calcium carbonate. We're also looking at barium sulfate and iron sulfides. And we looked at this at different scales. I'm going to start with the results of the molecular dynamic simulations. These were done a while ago when we were still using DL poly mostly. And this work was done by Sergio Ruiz Hernandez. And it's important to realize that these simulations were done on, of course, much smaller systems and much higher supersaturations than the experimental results I will show next. But what we saw was, if we have a perfectly stoichiometric 1-to-1 calcium carbonate solution with all the ions fully solvated, and then within 20 nanoseconds, we see this kind of large cluster sizes forming. Well, if we have even a very mild difference in calcium to carbonate ratio, we see a big impact with much smaller clusters forming. It's important to note, though, that because of the electrical charge neutrality issue with the Ewald summation that Paolo also mentioned before, that we also struggled with this, of course, and what we did, we solved it the way we do as experimentalists as well. If you're making non-stoichiometric solutions, you will also increase either sodium or chloride, because those are the salts that you're putting together. And so in the non-stoichiometric experiments, we will also have more of sodium or more of chloride. But we know from the work that Devis did a couple of years ago that these electrolyte ions actually influence the kinetics of the system. So it might be that we see different behavior because of the sodium or the chloride present, but it could also be the stoichiometry. Anyway, we also looked at the same process with dynamic light scattering. And this is at higher carbonate, and this is stoichiometric, and this is higher calcium conditions. And what do we see in our experiments? At T0, which is the yellow curve, in the ideal conditions, we see immediately, and T0 is about 1 minute, because it takes a while to start the measurement and get the first results in this technique. We already have particles that are 10 nanometer in size, and then with time they clearly grow until they become too big to measure, which is this is about the maximum size you can measure in this setup. And they may also be settling to the bottom, and then we also don't see them anymore. And then we are left with the signal of the ion pairs in the solution. This is a relative number percent scale, so that's why suddenly this peak, which was always there, is the one dominant peak. And if we then look at the non-ideal ratios, we see in both sides, both extremes, that the particles for up to 3 hours remain below 10 nanometers. So while in the ideal conditions we see probably aggregation, also growth, and we know transformation because we start with making amorphous calcium carbonate and we finish with calcite crystals from different techniques. We see that in the non-ideal ratios, we see that the stable nuclei remained for a very long time. And how can we link the MD with the DLS? We did that by plotting a probability curves. So what you see here is on the y-axis of all the graphs, the probability of finding ions in your system in clusters that are either very small or up to about 400 ions in size. And the first three are from MD, and in all cases, so this is our work and this was a published work, the cluster formation was observed within 20 nanoseconds, and this is our DLS results at time t is 0, which is about a minute actually. And so for the MD results, in all cases of these simulations, they started with fully solvated systems and they all observed clusters of cluster formation within 20 nanoseconds. And in Smeets et al., which is the highest degree of supersaturation, they observed particles of about 400 ions in size and some small particles. And they interpreted their results as a process of dense liquid formation, where the ion pairs and clusters are feeding into the large dense liquid phase. And in our work, we see a similar distribution, although it's not so clearly developed yet, but it's also at lower degree of supersaturation. And we think that we have essentially the same process, but because we're at lower driving force, this takes more time. And we're still in the process of the development of this bimodal distribution. And then, sorry, my apologies. In this work, there is, I'm sorry, I'm gonna drink some water. Okay, right. I'm going to try and keep talking. I'm sorry that it might sound not so pleasant. Okay, and so here in this simulation, the distribution was not so broad yet. It was also for a smaller system, we think. But this is again at a much lower degree of supersaturation. So maybe we're still seeing the widening of the distribution. So we may actually have different snapshots of the same dense liquid formation. And now if we look at the DLS, we are now at much lower degree of supersaturation, but we're still in the realm of amorphous calcium carbonate, which might be considered a dense liquid separation, but I think that's still not entirely resolved yet. And what we see here is that with decreasing degree of supersaturation, we see that the distribution widens. So we see particles that are very small here and much larger here, which makes sense if you look at crystallization mechanisms. If you have a very high driving force like here, you'll have lots of nuclei forming rapidly, so you end up with many small particles. But if you're in a less supersaturated conditions, you will have less nucleation and more growth dominated system, and that's what we think we see here. And then going to this one here, we cross the boundary of the solubility of ACC, so we think we're undersaturated with ACC, and now we're in a calcite system. And so we have the same trend that we see here, that we think would be here as well, where we would see widening of the distribution again if we would go to even lower degrees of supersaturation. And so in this case, we see ACC, and here we have the switch from ACC to calcite. If there's still time, Davis?
We probably have just a few minutes.
Okay, yeah, this is the last slide with the results. We also looked at the same process with cross-polarized light microscopy, a very simple, humble technique in dark field. So you don't see anything as long as there's nothing crystalline. And as soon as you see crystals appearing, you know that they've grown to about 20 micrometer when it's calcite because of the optical properties and the refractive index. And so we timed how long it took to see at least 2 crystals at different degrees of supersaturation and different stoichiometry again. And we see that there is a clear dependency of this time. This is precipitation time in seconds. And so especially in the area where it's still without ACC formation, so those are the purple and the blue lines and the red line, we see there is a clear asymmetric dependency of the formation of the calcite crystals. And so this is nucleation plus growth. And this asymmetry shows that actually an excess of cations more strongly inhibits particle formation than an excess of anions. And this dependency flattens out when we go to the very high degrees of supersaturation, and that also makes sense if we go to some dense liquid-like phase separation, where it's a different process from the nucleation plus growth that we are looking at here. And so what we see in this part of the work, we see that the calcite nucleation depends on solution stoichiometry with faster aggregation and growth at the 1-to-1. And at non-stoichiometry, we see that that nuclei are stabilized, and we suspect that it is charge stabilized colloid kind of behavior, because we know from zetopotential measurements now that these carry a charge, a surface potential, and the same behavior we see for the formation of larger calcite crystals. And we think we can compare MD and DLS results by using a probability distribution way of plotting. And with that, I would like to thank you all for your attention. And are there any questions?
Okay, thanks a lot, Mariette. So we think we have a few minutes to ask a few questions to Mariette. If anyone would like to, again, to just write on the chat or unmute and ask a question to Mariette. So while we wait that, I've got at least a couple of questions, but I will just go for one for the moment. It's about the first part where you talked about the variability of the hydrodynamics as a function of the surface topography. Mm-hmm. And you show essentially that is the reactivity that controls the dissolution. It's, if I remember correctly, this kind of matches very well with also the growth that occurs on these particular regions of the surface. Am I correct? So can we say that dissolution and growth are one opposite the other, or is that an oversimplification?
I think we can make that simplification. Although when I said it at the British Association of Crystal Growers, that dissolution is the reverse of growth, they didn't really like it. So it depends on who you talk to, but in my mind, it's the same. And of course, the processes can be different, but with ions or clusters coming in and ion detachment. And so I focus now in the talk mostly on the free energy of the extraction of the ions, but previously in the work that we did together, of course, I showed that if you compute the water exchange frequencies over such a rough surface, there's a 2 order of magnitude variability in water exchange frequencies over a surface with an island. And so perhaps the force fields I used there were not actually accurate, but I think that kind of variability over the surface is it makes sense, and it's also been confirmed by others. And maybe that also contributes to the rate spectra besides the extraction energy itself. And of course, I guess the extraction energy will be affected by how the dynamics around that ion changes. Yeah.
Okay, thanks. Do we have any questions for Mariette? Otherwise, I ask another question that is related to something I didn't fully understand, was because you talk about we look at the different percentages of magnesium on the dissolution of calcite. I didn't understand why do you think there is an increase in edge-speed nucleation as you have a low magnesium content, and now this could affect the dissolution rate.
Mm-hmm.
So
yes. So if you look at a bulk dissolution rate of calcite, what you measure is how fast the calcite surface is being stripped away. And that happens via different mechanisms. So it's the combination of edge pit nucleation and edge pit widening, the trains of steps, the wormholing maybe even. So it's a sum of different mechanisms that all end up in this bulk dissolution rate. And if you can't trigger edge pit nucleation, you will then also inhibit the next step, which is stripping away the edge pit edges.
Okay, okay, thanks a lot, Mariette, for that. So okay, so if there are any other questions, so we are just like, run out, but it's okay, no problem with that. And I just would like to thank again Mariette and Paolo for their talks, and for the other people for attending the event. And yes, I mean, if Paolo and Mariette want just to stay for a while for a very quick chat, or anyone else as well, yeah.
I actually would like to have dinner.
That would be, that's a good one.
And the beer.
That means you're not eating in front of your computer, which I'm sure has happened before.
Yeah, I'm also wearing pants.
I'm not.
I don't know.
I'm just kidding. Come on.
Want to see.
Anyway, can I just express a thank you from everyone to Devis for organizing this. So thank you, of course, to our speakers as well, but thank you, Devis.
Yeah, well, it's just, as I say, this is, but thanks a lot for Paolo and Mariette. And this, we organize quite a lot of this type of events at the TYC. And I'd like to thank Karen, who I think she left already, for helping me in doing this. And I know that Karen is there. Okay, yeah, great. If Paolo and Mariette can just stay for a while, and Greg as well if you want, because Paolo, I think if we have a project with Mariette and Greg on magnesium carbonate. So if by any chance you pass through London.
Yeah, I have some friends that live there, and they invited me just last week again. But yeah, we'll see. I'm happy to. I will for sure get in touch.
So it would be great to have a bit of have your brain on a few things, even technical things such as I've seen that you have used, for example, a lot of amoeba force fields, and that we haven't used. So and I've seen that you have used this OpenMM code to use amoeba. So so is it how universal is this amoeba? Is it easy to apply? Is it as easy to apply as, for example, the amber force field, but really more accurate?
No, it's not that easy because it's not as widely used. So the main difference for me is that lamps, for example, ODL Poly or NAMD, Gromax, are just packages. You get your input file, you get your force field file, and then works. OpenMM is a library. So I had to write a Python code that is actually an MD code that calls OpenMM libraries to do all the things that molecular dynamics code does. So
okay, so OpenMM, sorry, I got confused. OpenMM is actually not an MD code; it's an open molecular mechanics database. Let's go like that.
Well, it is a Python, a C++ library, and then you can create your own MD code in C++ that calls all the libraries in OpenMM, or we did it in Python because the Python interface connects with Plumed. Instead the C++, you have to write your own thing. So the first line is, read the coordinates file. Then the second line is read the force field, then generate the topology, then call the integrator to do. And so it's a bit, the learning curve was significantly steeper than any other MD code that I've ever used. But now we have a functioning thing. And similarly, developing the force field is a bit more complicated because, as Alston mentioned before, you have to fit these multiples, so you have a more complicated starting point. And then the other thing that is annoying us is that you're basically forced to use combination rules.
Mm-hmm.
And so if we want to develop a specific calcium carbonate interaction, you cannot put it directly into the amoeba force field.
Okay.
So what you can do in Python though, because OpenMM is extremely flexible, you can define your own force field term and then apply it through Python to a specific ion pair. So it is a bit harder to use, but it is very fast on GPUs because we do normally 10 nanoseconds a day on a Volta GPU using maybe 50,000 atoms. So it's comparable to lamps, maybe 2 times, 3 times slower than lamps.
But I haven't read the detail your paper on your last paper on ACS Earth Science, but you've got a force field for magnesium carbonate, isn't it now working?
Yes. Yeah.
Okay. So I have actually a student that I've sent a student now to CISA to try to develop a force field, machine learning based force field for magnesium in water. Probably probably you know the work of Alessandro De Vita that unfortunately passed away. Yeah. And so there is Stefano De Girocoli took up that the project. Yeah. And so I have a student that tried to do that to see what if you succeed.
Giovanni is the person I know best at CISA, but I've heard of most of the people there.
Okay.
But look, if you want, we can organize an online another meeting at some other place.
It would be good.
Whenever is more convenient.
Okay.
Early
great.
morning for you and afternoon for me.
Yeah, great. And okay, so well, thanks a lot, Mariette and Paolo, and hopefully I will see you. Well, I will see Mariette probably at the next funding meeting, and Paolo, I hope to see you. Yes.
Can I just sorry to jump in? So Paolo, what we're seeing more and more is these grants, these fundings, or these opportunities. Money. We're always writing grants. There's more and more opportunities. People are always saying, multidisciplinary, international, blah blah blah. But they're really ramping up on these kind of things, especially with EU funding. Also in Italy, MIOR and the PRIN grants and opportunity, etc. And ourselves with our projects. I mean, I started out as a computational theoretical chemist obsessed with entropy. Don't get me started. Now, publication, it matters much less to me now because of the work with industry, which is ramping up like this. Engineering, these kind of grants. Now, there's a whole slew of grants that have nothing to do with papers, academia. To me, it was, industry used to be, the dark side of the force. What I've discovered, a lot of these industrialists, they're desperate for solutions. At first, maybe they had to do it because CO2 or climate change or products or output or profit. Now, a lot of them are really, now they're really on board. So we do mineralization also of cement because you do get different mineral phases. We're doing the CO2 mineralization, magnesium carbonates and otherwise. Some of these people they're all right. They're not the dark side of the force. They're just joking aside. No, I mean, so, going from being a theoretical chemist, publishing about entropy and low energy vibrations, now forming solutions on multi-kilo scales. Theoretical chemists deal with pure systems and pure environments. Yeah. We're dealing with, it's 95% pure, good enough. That was appalling to me 15 years ago. Now I'm seeing that we're actually helping these people make solutions. Get to the point, Greg. The point is, we really need, and some of these grants require external, international, industrial partners, not just in name to tick a box. They want to see activity. We've got that now. And, we know Mariette and her activities already. Yourself, I know it's something familiar with, but, making these sort of, joint projects. Australia is Commonwealth, even though the Commonwealth is just a sort of figurehead. Canadian, I have Canadian connections. So, you put these kind of proposals in and we do get the time or the money to see each other or work together. So maybe we do try to pursue something like this, online at first, and then seeing where we can do something small together at first. So I would really love to see that happen.
Yeah, absolutely. I'm always happy to be involved and help if I can, do collaborations with experimental.
Well, I've been really surprised.
Everyone.
I've been surprised by the response from industry. We give them tiny little bit of, direction. They're very happy. The response is very positive.
In Australia, getting industry money, it's a bit hard because we don't have that much industry research. I mean, they dig up a hole, they find
Sure they do. They're just not giving it to you. And what they call research is not the same, but we need to speak their language. I've been recently to the gravel pits. I mean, we're talking big, dirty place where they recycle cement and stuff. You'd think these people aren't listening. They got tons of money and they need. Anyway, we'll talk more about that later, in discussions. But, I'm surprised the response, but we need to speak their language. They don't want to hear entropy and low energy, cooperative, collective vibration. They don't understand that. They
want to get money.
ISO standards and stuff. So I'm learning that language and they're really responsive. And, oh, yeah, we'll try. Okay. Boom. We have a few thousand. We could maybe find 10,000 for that. Is that enough? We're like, yeah. Anyway, so
good. Yeah, just let me know if you want to write something together.
Dennis, like you said, we'll try to have a chat again soon, and I'll report on my activities if you like. Then we'll see where we go from there. You need dinner. You need food.
I do. And I need beer. It's still.
I need beer. He's becoming Australian.
29 degrees here outside. It's 8:30 p.m.
Well, it's degrees here in
it's
sunny.
Almost summer there, I suppose.
Yeah, it's the end of summer.
The end of summer.
Okay, thanks a lot. Thanks,
David, for the invite. Davis.
I will maybe send you. I will send you an email, Paolo, about maybe Mariette. I will include Mariette. Maybe some of these people would like to be interested to know about this open MM.
Absolutely.
Yeah.
Thank you, Mike. Thanks, Paolo. Thanks,
Davis. Bye, guys.